My name is Stephanie Hicks, and I'm an associate professor of biostatistics and biomedical engineering. I joined in February of 2018, and before that I was a postdoc at Dana-Farber Cancer Institute, and there I did my postdoc with Rafael Irizarry, and so whenever I was there he told me about all the great things about Hopkins biostats, and so when I went on the job market, it was a really great place to come to. Oh, so many things. If you are math-oriented, CS-oriented, engineering-oriented, statistics, biostatistics in particular, is a great space to be able to apply your quantitative skills in a public health setting. And for me, that's working on problems around human health and human disease. I work on developing computational methods to help people understand very messy, noisy biological data at the cell level. My research interests are to develop computational tools for genomics data, and I do that at a single cell resolution. So the idea is if we have, say, two groups of samples, somebody who is a neurotypical sample, a set of neurotypical samples, and a set of samples who have Alzheimer's, for example, my research is to try and understand what the differences are by developing computational tools to help us figure out what's noise and what's signal, what's real and what's not real. And so if we can develop computational tools that help us remove the noise, then we can see the signal more clearly, and we can understand what the differences are, and then hopefully develop drug targets and things like that. Growing very fast. The reason is because, as you know, the world around us is becoming more data-driven, data-oriented, and it's exactly the same for genomics. We are generating very large data sets across thousands, millions of individuals, and so we're at a point where these computational tools are really essential to be able to figure out what's noise and what's real biology that's driving, for example, different human diseases. So for me, the field is only growing bigger, mostly because of the opportunities for data availability that we didn't have 5 years ago, for example. And it's a very exciting field to be, because even very simple statistical ideas can have a huge impact in a field that's brand new. So a lot of people ask me about what's going to happen with AI in 20 years. I don't know. It's very hard to know. But I do know that we are going to solve a lot of diseases in the next 20 years. And the reason I know that is because we have the technology now to solve them, and we have the ability to actually investigate that data also that I talked about at the beginning. So not only can we measure the data that we want to measure, we can also, we have the data that we have generated, and I know that because of the technological advances in both experiment and computation, that we are going to solve a lot of disorders in the next 20 years. So my hope is that the computational tools will just play a small part in that larger picture of solving a lot of human health or human diseases. It's incredibly collaborative, so I don't have to cross institutes. It's all one big institute. I just email someone in another department and I say, "Hi, I'm Stephanie, can we work together?" And almost always they say yes. I teach statistical programming paradigms and workflows, and the idea is to help students who do not have computational background, give them a best practices kind of overview of the really essential computational tools that they'll need to do for their, they'll need to have for their research. It's one of the coolest spaces to be in, because if you are interested in a quantitative background, if you're math-oriented, if you're CS-oriented, one of the things that you might find is challenging is that how do you have an impact in the real world? And biostatistics, the intersection of biostatistics and public health is a great space to be able to have that impact.